Alright, so we have the block is already slid down the hill. Right? So it slides down a hill and enters a surface that is smooth, or not smooth rather. Maybe it's okay. Enters a surface that provides a resistive force of some kind. And you're told that the resisted force that is provided on the block all the way along this rough horizontal surface is given by F equals beta speed squared. It's a resistive force, so it's always in the opposite direction of the velocity. So the object slides downhill. We would use conservation of energy to figure out how fast it gets to the bottom of the hill. And then we're asked to find out what is the function for the velocity as a function of time as it slides along the surface here. The velocity function at all times is governed by the forces that are acting on the object. So if it starts with some initial velocity v0, what will the velocity be later on is influenced by the presence of this force at all times. Together? So we consider the forces on the object. We have normal force, of course, that's always there. You have gravitational force. No, you cannot. I'm going to tell you why. You cannot use anti-differentiation, because when you write down Newton's second law, you're going to go, the force is a resistive force, so we're going to write minus b v squared is equal to ma. The minus sign just means that the acceleration is always in the opposite direction of the velocity. We keep the minus sign here because we're trying to make sure that this predicts an outcome that is consistent with the force always being in the opposite direction. Okay, so that's the need for the minus sign. Okay. Now, if you just solve for a here, you'll get a equals beta v. You do not get a as a function of time. The only way you can do this, Summer, is if you have an integral of a function that's already a time-based function only. But to solve for a here, you get, what would you get if you solve for a? There's no t, so you're done for. Exactly, there's no t. So in order to get t and be still focused on the variable v, is we make a substitution for a, which is dv dt. Okay, that's the first step. That's the only thing that produces t's. Next step involves taking this expression and moving around the variables of interest. The variables of interest is t and v, but they're linked right now. We need to not link them. So we literally just treat this as a fraction. Move the dt to one side. Leave the negative beta over there. Also bring the m with it. So divide m over. What's still left over here? dv over v squared, exactly. Okay. So now we're pretty close. Now we say, okay, we're trying to solve for the function v as a function of time. So it requires we first integrate both sides to undo the dt's and the dv's, in a way. You can think of it as that way. A math teacher would articulate why is it that this process is done this way, and I'm not going to spend time trying to support that. But the idea is what we're doing is we're trying to solve for the function v, and whenever you have an expression that has a first derivative of a function, and the function also mixed in on one side of the equation, you need to somehow get all the variables together. So we call this separation of variables and group them collectively together. So dv goes with v. Now v started out at some initial velocity that the block has. And eventually it's going to reach some final velocity. What do I mean by some final velocity? Some velocity later on. Okay. So ultimately in the end we're actually solving for vf. Well, what's time doing? How does time start? Time starts at what? Time equals 0. And what will time eventually be? Some t final. So that's just adding some upper limits and lower limits to my integrals. And that's just taking the physical parameters as my guide. The left side, I simply have negative beta over m. They're constants. Pull it out of the integral dt from 0 to t pi. Still over here, I've got the integral from v0 to vf 1 over v squared dv. I'm writing it that way so it's clear how we actually pursue the antiderivative. This doesn't look like a v at all. Together? In the separate set, it makes it clear what happens next. On the left side, it's easy. I have like a 1 in front of the dt, correct? So what's the antiderivative on the left side? Just t. So you get t evaluated from 0 to tf. Yeah, I can. Give me a second. Those suckers are just constants, right? Beta and m. This is just the differential component of an integral, correct? So if there's like a t in there next to it, you'd say t squared over 2. If it was t squared dt, you'd go t cubed over 3. But I only have a imaginary 1 that's holding that position. Or think of it as t raised to the 0 power. So it becomes t to the 1 over 1. Or what do you take the derivative of to get 1?
Oh, it's like 0.
Yeah.
Because it's so
No,
small.
no, no, no. All we're doing is asking what's the antiderivative of 1. What do you take the derivative of?
Oh.
1t. Yeah, so the derivative, yes. Yeah. Well, let's come back to that, just so we can make it clear later. Almost there, though. On this side, what do we have? Actually, I need to take the antiderivatives. Before I do that, I'm going to rewrite it, actually, so I won't erase it. This is like writing v to the minus 2 dv. Agreed? So what does the antiderivative on the right side become? Yeah, negative v to negative 1. So you add 1 to the power, v to negative 1, and you divide by what you get in the power. Divided by negative 1, this produces a minus sign. We put all that, and we evaluate it from v0 to v final. Okay, so that's what that step produces on the right side of equal sign. Let's continue the right side for now. We get, of course, this is like negative 1 over v, correct? Agreed? V to negative 1 is 1 over v. So I plug in v final, I get negative 1 over v final minus negative 1 over v initial. Agreed? On the left side, I simply have minus beta t final over m. Okay. The task still is solve for v final, but the question actually just wants you to write it in the form you have right in front of you. You see that this becomes plus plus? Move the 1 over v final to the left side of the equal sign, and move this constant term over to the right side of the equal sign. And this is all the exercise wants you to write. That in that form, the final velocity, or the velocity at some time later, is given by that expression. You're done.